Hello folks, I'm going to talk tonight about the history of Scottish geology. When I retired, I used to go out in the countryside for a nice wee walk round, and I'm quite sure, like a lot of you, when I was out there walking, I thought, it kind of all looks like this. So I decided to go back home and do what most people do and look up Wikipedia to find out why it looked like that. Kind of got me interested, and I started going to geology classes as well. Back a couple of thousand years ago, you couldn't look up Wikipedia, it didn't exist. And there wasn't any shoulders of giants to stand on, so you would have to try and maybe work it all out for yourself. So try and put yourself in the position of the people a couple of thousand years ago who didn't have the sort of knowledge that we can easily find out from books. Try and pretend you're somebody trying to work this all out for the first time. So you have a look around, you saw those hills. If you get down to the coast, obviously you wouldn't see all the houses, but there would be people living on the coast. There'd be rolling landscapes, and there'd be this strange mountain that smoked that they called a volcano. So, at the end of the winter, you decide it might be a nice idea to walk up to one of these mountains and try and find out more about it. And as you're walking up towards it, it's the spring, so snow's been melting and rocks have been breaking off the sides of this crevasse, and if you look down at the rocks in the water, they're really quite sharp because they've just broken off. They haven't been thrown about much. As you start, remember you had to get back home, so you start walking back down the river, and you see as you go down, first the rocks, because they've been tumbled about a bit, start to get a wee bit rounded corners. And as you walk even further down the river, some of the boulders have been smashed up, and the pieces tend to get smaller and more rounded. And you walk even further, again, all the rocks become even smaller and even more rounded. And as you walk right to the end of the river, you might come across something like this. It's a delta. So it's very, very fine pieces of rock. Or you might land up at a beach. And you can see, obviously, what we call sand. It's therefore easy to understand that mountains get smaller as ice in winter breaks up the rock, which washes down the rivers to become small rocks, and then eventually sand. So the question is, how did the mountains get in the first place? I mean, did God make them like that? The rocks shown in this slide are fairly obviously also made of sand, so how did the sand become stone? This slide also shows different layers of rock, but it's kind of hard to understand from this how, if it's a mountain that's been washed down into the sea, why is it two completely different types of sand that have got crushed together to make this stone? The people who thought that all rocks were formed by river deposits that had washed down into the bottom of the ocean and then solidified were called Neptunis, after Neptune, the god of the sea. And mind you, this rock doesn't look like it got to the bottom of the sea, does it? This looks much more like the sort of stuff you see at the bottom of rivers. And yet it too is very well-rounded pebbles, so it's obviously a very big river to throw them about like that. And maybe in big rivers the sand gets down to the bottom and that's what causes it to sedimentate. I don't know. So now, we're now going to have a look at some of the early great thinkers of Scottish geology to find out how they developed their ideas from the evidence that they could see in the Scottish landscape. James Sutton was born into a well-to-do family in Edinburgh on the 3rd of June 1726. His father was a wealthy merchant who was also the Edinburgh city treasurer. Hutton's father died in 1729 when he was 3. He was educated at the High School of Edinburgh, where he was particularly interested in maths and chemistry. Then, when he was 14, he attended the University of Edinburgh as a student of humanity, studying the classics. He was apprenticed to a lawyer when he was 17, but took more interest in chemical experiments than legal work. At the age of 18, he became a physician's assistant and attended lectures in medicine at the University of Edinburgh. After 3 years, he went to the University of Paris to continue his studies, taking the degree of Doctor of Medicine at Leiden University in 1749 with a thesis on blood circulation. After his degree, Hutton went to London, and then in the mid-1750s returned to Edinburgh and resumed chemical experiments with his close friend James Davy. He was therefore very well travelled and a highly educated individual. Unfortunately, like Robbie Burns, he was also a bit of a jack-the-lad, and after one unfortunate pregnancy too many, he was advised to leave Edinburgh society urgently. So he became a gentleman farmer on the family estate in Berwickshire. Once he moved there, he set about making improvements, introducing farming practices from other parts of Britain and experimenting with plant and animal husbandry. He recorded his ideas and innovations in an unpublished treatise on the elements of agriculture. This developed his interest in meteorology and geology. In a 1753 letter he wrote, "I've become very fond of studying the surface of the earth, and I was looking with anxious curiosity into every pit or ditch or bed of a river that fell in my way." Clearing and draining his farm provided ample opportunities. The mathematician John Playfair described Hutton as having noticed that a vast proportion of the present rocks are composed of materials afforded by the destruction of bodies, animal, vegetable and mineral, of more ancient formation. His theoretical ideas began to come together in 1760. While his farming activities continued, in 1764 he went on a geological tour of the north of Scotland with George Maxwell Clark, ancestor of the famous James Clerk Maxwell. In 1785, at Glentilt in the Cairngorms, Hutton found granite penetrating metamorphic schists, in a way which indicated that the granite had been molten at the time of intrusion. This demonstrated to him that granite formed from the cooling of molten rock rather than precipitating out of water, as others at the time believed, and therefore the granite must be younger than the schists. Patton then started searching for further evidence that rocks hadn't simply been laid down on top of previous older layers of rock. I'm afraid I couldn't really find a good photograph for this one that I could use, but this rock in the middle is actually quite pink, and that's the granite, and these are the grey schists on either side. So what Patton was saying is it was obvious to him, there's more granite there, that this had all pushed up through the schist. So this must be younger than that. He went on to find similar penetration of volcanic rock through sedimentary rocks in Edinburgh at Salisbury Crags, adjoining Arthur's Seat. This area of the crags is now known as Hudson Ascension. He found other examples in Galloway in 1786 and on the Isle of Arran in 1787. His idea was that mountains were built up, then eroded away, then built up and eroded away. So it was possible for there sometimes to be no record of the different layers of rock that once existed. This is called an unconformity. The right-hand photo is Hutton's unconformity on Newton Shore in Arran. The almost vertical rocks in the foreground here are Doriadan schists, which are about 520 million years old. The rocks in the background lying over them are Kinnisuit group sandstones, which are about 360 million years old. The missing time along that wee area there is about 160 million years. In the spring of 1788, he set off with John Playfair to the Berwickshire coast and found more examples of this sequence in the valleys of the Tour and Peasburns near Coburnsburg. They then took a boat trip to Dunglass Burn, east along the coast, with the geologist Sir James Hall of Dunglass. This found the sequence in the cliff below St Helens, and just to the east at Sicker Point, found what Patton called a beautiful picture of this junction washed bare by the sea. Playfair later commented about the experience. The mind seemed to grow giddy by looking so far into the abyss of time. Continuing along the coast, they made more discoveries, including sections of the vertical beds showing strong ripple marks, which gave Hutton great satisfaction as a confirmation of his supposition that these beds had been laid horizontally in water. Hutton reasoned that there must have been innumerable cycles, each involving deposition on the seabed, uplift with tilting and erosion, and then the sea again for further layers to be deposited. On the belief that this was due to the same geological forces operating in the past, as the very slow geological forces seen operating in the present day, The thicknesses of exposed rock layers imply time in truly enormous stretches of time. Because of this, Hutton is credited with originating the concept of deep time. So if you can manage it, and it's not easy to get to because you've got to lower yourself down a side of a cliff using a rope, but this place, Sicily Point, is gorgeous, and the red colours on a sunny day are fabulous. I've been there 3 times now. But essentially, as you can hopefully see, this is obviously sedimentary. You can see all the layers. And up until now, everybody has said that sedimentary rocks is just laid down like that on the sea surface. So what Hudson was saying is, for something like that to get like that is obviously going to take a long time and require fairly vast amounts of forces. And once it's been there, he then reasoned it must have sunk back down under the sea for this layer here to then come along and be laid down on top. So you got horizontal layers on top of vertical layers, even though it was all sedimentary style rocks. John Playfair was born in Benvie. Let's move this up a bit, slightly to the west of Dundee. He was educated at home until the age of 14, when he entered the University of St Andrews to study divinity. He also did further studies at Edinburgh University. In 1773, he was licensed to preach by the Church of Scotland. However, Playfair chose to continue his studies in maths and physics, and in 1782 he resigned his charge to become a private tutor to the gentry. By this arrangement, Playfair regularly visited Edinburgh and went on to cultivate the literary and scientific society for which the city was at that time specially distinguished. Through Neville Maskelyne, whose acquaintance he had made in the course of the celebrated Schiehallion experiment in 1774, which we'll come to later, he also gained access to the scientific circles of London. In 1802, Playfair published his celebrated volume entitled Illustrations of the Huttonian Theory of the Earth. The influence exerted by James Hutton on the development of geology is thought largely to be due to this publication. Sir Charles Lyle was a Scottish geologist born the year after Hutton died, who demonstrated the power of known natural causes in explaining Earth's history. Principles of Geology, Lyle's first book, was also his most famous, most influential, and most important. First published in 3 volumes in 1830 to 1833, it had established Lyle's credentials as an important geological theorist and propounded the doctrine of uniformitarianism. It was a work of synthesis, backed by his own personal observations and his travels. The central argument in Principles was that the present is the key to the past, a concept of the Scottish Enlightenment which David Hume had stated as all inferences from experience suppose that the future will resemble the past. Geological remains from the distant past can, and should, be explained by reference to geological processes now in operation and thus directly observable. Lyle's interpretation of geological change is the steady accumulation of minute changes over enormously long spans of time, was a powerful influence on the young Charles Darwin. Lyle asked Robert Fitzroy, the captain of the HMS Beagle, to search for erratic boulders on the survey voyage of the Beagle, and just before it set out, Fitzroy gave Darwin Volume 1 of the first edition of Lyle's Principles. When the Beagle made its first stop ashore at St. Diego in the Cape Verde Islands, Darwin found rock formations which, seen through Lyle's eyes, gave him a revolutionary insight into the geological history of the island, an insight he applied throughout his travels. Yeah, as we said right at the beginning of this talk, these guys weren't standing on the shoulders of giants, they were the giants, so sometimes they got it wrong. In Principles of Geology, Lyle proposed that icebergs could be the means of transport for erratics. An erratic is a piece of rock of a completely different composition to the country rock it stands on. He thought that during periods of global warming, ice breaks off the poles and floats across submerged continents, carrying debris with it. He thought that once the iceberg melted, it rained down sediments upon the land. Nowadays, we call these rocks glacial erratics, as we can now prove they're actually dropped when glaciers melt. Furthermore, Lyle believed that the accumulation of fine angular particles covering much of the world, called loess, was a deposit settled from mountain floodwater. Again, we now know that these were actually formed in desert environments, but Lyle couldn't know that the continents themselves move over the surface of the Earth. That said, many of Lyle's mechanisms for geological processes have stood the test of time. His observational methods and general analytical framework remain in use today as foundational principles of geology. Lyle's work on volcanoes focused largely on Vesuvius and Etna, both of which he'd earlier studied. His conclusions supported the idea that volcanoes built up over very long periods of time, so-called backed up building, as opposed to the sudden upheaval argument supported by other geologists. As I mentioned earlier, John Playfair had been involved in the famous Schiehallion experiment. This was a project to determine the mean density of the Earth. Funded by a grant from the Royal Society, it was conducted in the summer of 1774 around the Scottish mountain of Schiehallion in Perthshire. The experiment involved measuring the tiny deflection of a pendulum due to the gravitational attraction of a nearby mountain. Schiehallion was considered the ideal location after a search for candidate mountains, thanks to its isolation and almost symmetrical shape. The experiment had previously been considered but rejected by Isaac Newton as a practical demonstration for his theory of gravitation. However, a team of scientists, notably Neville Maskelyne, the Astronomer Royal, was convinced that the effect would be detectable and undertook to conduct the experiment. The deflection angle depended on the relative densities and volumes of the Earth and the mountain. If the density and volume of Schiehallion could be ascertained, then so could the density of the Earth. Once this was known, it would in turn yield approximate values for those of the other planets, their moons and the Sun, previously known only in terms of their relative ratios. As an additional benefit, the concept of contour lines, devised to simplify the process of surveying the mountain, would later become a standard technique in cartography. Maskelyne came up with a figure around 4,500 kilometres per cubic metre. In comparison with the modern accepted figure of 5,515 kilograms per cubic metre, the density of the Earth had been computed with an error of less than 20%, just by using a pendulum. The Schiehallion experiment was repeated in 1856 by Henry James, the Director General of the Ordnance Survey, who instead used the hill Arthur Seat in central Edinburgh. With the resource of the Ordnance Survey at his disposal, James extended his topographical survey to a 21-kilometre radius, taking him as far as the borders of Midlothian. He obtained the density of around 5,300 kilograms per cubic metre. This is incredibly close to the 5,500 we mentioned earlier. A modern re-examination of the geophysical data of the Schiehallion experiment was able to take account of factors the 1774 couldn't. With the benefit of a 120-kilometre radius digital elevation model, greatly improved knowledge of the geology of Schiehallion, and in particular a computer, a 2007 report produced a mean Earth density of 5,480 plus or minus 250 kilograms per cubic metre. When compared to the modern figure of 5,515, it stood as a testament to the accuracy of Maskelyne's astronomical observations. We've had a look at how people were looking at rocks and trying to understand how they formed. We'll come back to look at some of the answers later. For now, let's take a wee side trip into the world of fossils. Sadly, nobody Scottish of note appears in the early story, so I'll have to go to the south of England for an interesting historical figure. Mary Anning was an English fossil collector, dealer and paleontologist who became known around the world for important finds she made in the Jurassic marine fossil beds on the cliffs along the English Channel at Lyme Regis. Her findings contributed to important changes in scientific thinking about prehistoric life and the history of the Earth. Anning searched for fossils in the areas of Blue Lias cliffs, particularly during the winter months when landslides exposed new fossils that had to be collected quickly before they were lost to the sea. She nearly died in 1833 during a landslide that killed her dog. Her discoveries included the first ichthyosaur skeleton correctly identified, the first two almost complete plesiosaur skeletons, the first pterosaur skeleton located outside Germany, and important fish fossils. Her observations played a key role in the discovery that coprolites, known as bezoar stones at the time, were fossilized species. She also discovered that belemnite fossils containing fossilized ink sacs, just like those of modern squid. When geologist Henry de la Beche painted Duria Antiquior, the first widely circulated pictorial representation of a scene from prehistoric life derived from fossil reconstructions, he based it largely on fossils Mary Anning had found, and sold prints of it for her benefit. Mary struggled financially for much of her life. Her family were poor, and her father, a cabinet maker, died when she was only 11. After her death in 1847, her unusual life story attracted increasing interest. It's often been claimed that her story was the inspiration for the tongue twister, "She sells seashells on the seashore." There are fossils to be found in Scotland, but most of the ones I've found have just been of sea-dwelling plants and limestone from local quarries. If you're looking for dinosaur remains, the best you're likely to see are these footprints found on Ancoran Beach on the Isle of Skye. And just in case you can't figure it out, it's a modern foot. And this is the three-toed foot of a dinosaur that walked across a wet beach a long, long time ago. And then the beach stopped being wet, it dried, and then print was kept. There are also some interesting fossilised trees to be seen here in Glasgow. Either visit the original site of Fossil Grove in Victoria Park, or see a removed fossil in the Kelvin Grove Museum. The trees in Fossil Grove are unusual in that they can still be seen in their original location in the heart of the city. I mentioned earlier that Charles Lyle couldn't know about the continents moving about on their surface, so I suppose I should give a bit more detail about how we come to understand this. It'll also be difficult to understand some of the Scottish features we'll be looking at later, unless you at least appreciate the continents have moved over time. Since the days of the first maps of the world, it seemed a bit odd that the left-hand side of the map looked like it fit snugly with the right-hand side. Things get even more odd when early fossil discoveries showed that fossils in Scotland were the same species as fossils in Canada, but completely different from the species of the same age found in England. It was as if Scotland and Canada used to be joined together, and Scotland used to be separate from England. Alfred Wegener thought about these sort of discoveries, and in January 1912 presented his ideas to the German Geological Society. His hypothesis was that continents had once formed a single landmass called Pangaea, before breaking apart and drifting to their present locations. Wegener was the first to use the phrase Continental Drift and formally published the hypothesis that the continents had somehow drifted apart. Although he presented much evidence for continental drift, he was unable to provide a convincing explanation for the physical processes which might have caused it. His suggestion that the continents had been pulled apart by the centrifugal pseudo-force of the Earth's rotation, or by a small component of astronomical precession, was rejected. His calculations showed that the force was not sufficient. Pretty much nobody believed his ideas had any merit at all. However, technology moves on, and we now have a mechanism that proved Wegener to be correct. This animation shows how we think the continents have drifted around over the Earth's surface over the last 250 million years. My favourite bits where India starts flying up, flashes into Asia, as we can see here. As the continents drift apart and crash into each other, huge amounts of lava are released to the surface of the Earth. To bring this talk back to Scotland, and also to get in some more pretty pictures, Here's the columnar basalt you find in the Scottish island of Staffa. Columnar basalts like this are formed when deep lava flows accumulate over a cold base, then cool and solidify from both the top and bottom surfaces. As deep lava cools slowly, cracks form in hexagonal shapes, resulting in what we see here. And here's the same columnar basalts that you find in the Giant's Causeway in Northern Ireland. These two sites haven't drifted apart. The feature actually continues under the Irish Sea. During the 19th century, Knocken Crag became the subject of much debate when geologists noticed that the moin schists at the top of the crag, just north of Ullapool, appeared to be older than the Cambrian Ordovician rocks, such as the Durness limestone, further down. Disagreements over the processes that could have caused this to occur were referred to at the time as the Highlands Controversy, which is a big talking point. National Heritage Scotland have built the visitor centre you can see on the right to explain to the public the words of Ben Peach and John Horn, who spent 1.5 years camped out in the worst of the weather the Highlands could throw at them, surveying and mapping the landscape to provide the clues to resolve the issue. The results of the mapping proved conclusively to Peach and Horn that the contact was tectonic. The recognition of the Moin thrust belt in the early 1880s was a milestone in the history of geology. It was one of the first thrust belts discovered, and where the importance of large-scale horizontal rather than vertical movement became apparent. Detailed mapping of the Moin thrust belt by the survey continued for another 2 decades, culminating in the classic survey memoir, The Geological Structure of the Northwest Highlands of Scotland, published in 1907. Hopefully you can see from the slide that the rocks at the top are of a different type from those at the bottom. Peach and Horn proved that they had actually been thrust 20 kilometres from their original position over the older rocks below. So how did this happen? Let's look at the movement of land around Ayers Rock in Australia. This is the classic photo of Ayers Rock in the sunset, but what I want you to note is that there are similar rocks in the background called the Olgas. Also, it's quite clear that the sedimentary layers of the sandstone that makes up Uluru are almost vertical. However, when we look at the Olgas, we can see from the close-up at the bottom left, the sedimentary layers are actually horizontal. Both Uluru and the Olgas are part of the same rock formation. So why is one part horizontal and one part vertical? Both outcrops are actually in the same formation, but the movement of the Earth's tectonic plates meant that over time, the part of the formation on the right-hand side of the slide was forced up more than the part on the left, so much so that it became horizontal. In the Moin thrust, the rocks couldn't bend, so one section was pushed over the top of the stronger continental rocks. Erosion of the surface layers means that some of the formation in the middle of the slide has disappeared completely, and the area generally has been filled in by more sand, covering up the evidence that it's all one rock type. Now, on to volcanoes. Most volcanoes are formed when ocean plates are driven under continental plates, although some can form in the middle of oceans over rising magma called a hotspot. The oceanic crust contains dissolved water. As it gets deeper, the rock begins to melt, and the water-infused rock begins to rise towards the surface. As it rises and the pressure decreases, the rock becomes less dense and more liquid, and eventually bursts through the crust as lava. If there's still a lot of water in the lava, these eruptions can be explosive. However, this presentation is based around Scottish geology, and there's no volcanoes currently erupting in Scotland. It used to be. Here's what a volcano looks like after it's been eroded for 340 million years. And here's what it looked like originally, we think. This is Loch Sunart in Ardnamurchan, near Fort William. Can you see the volcano? No, I can't, to be honest. How about we take a look at it from here? And this is why people create geological maps. Careful observations underground, followed by drilling boreholes to bring samples up from the depths, allows geologists to create the maps that illustrate the origins of the landscape we see here today. And an even bigger volcano has been eroding for even longer here. Can you recognise anywhere? No? It's actually the Black Coolins on Skye. It's now thought that the whole of Skye is really just the remaining stump of a huge volcano that exploded catastrophically about 560 million years ago. This explosion made Krakatoa look like a damp squib. There is evidence that the amount of gas and dust blown into the atmosphere led to an increase in global temperature of about 8 degrees Celsius, 4 times the increase predicted to create huge problems for us present-day humans. Driving through Scotland from the south shows fairly dramatic and sudden changes in scenery. It doesn't really look like it from the diagram, but the Highland boundary fault, separating the Highlands from the lowlands, that's it there, bends down through the middle of Arran and out into the northern Ireland. This is why the north of Arran is mountainous and the south flat. It also gives a clue to why Staffa and the Giant's Causeway are so similar. This slide again emphasises that Scotland and England were once literally different continents. We've seen on earlier slides what happens on the large scale when continents collide. Let's now look what happens on a smaller scale. These are the oldest rocks in Britain and are called Lewisian gneiss, after the island of Lewis. They were formed when the early continents of Laurentia and Baltica, we saw on the last slide, collided, forming the Caledonian Mountains, all the way down the east coast of Canada and the USA. This happened between 3 and 1.5 billion years ago. When the Atlantic Ocean started to form about 200 million years ago, a small chunk broke off and landed up attached to what's now Scotland. And this is the sort of thing that we go out on excursions as geologists to have a look at. Intense high pressure underground makes rocks into pretty much plasticine. So you can imagine a flat area somewhere, and this pressure as continents are moving aside, bumping into each other, and slowly deep down, maybe even 10 kilometres or so, the pressure builds and these rocks get pushed together, in this case, and pushed together and pushed together. Still pushed together and still pushed together until this bit is like that. Of course, they're still being pushed, so eventually it falls over. You get the sort of shape you can see in front of you on the screen there. The southern uplands consist mainly of Silurian sedimentary deposits dropped in the Iapetus Ocean about 500 to 400 million years ago. These rocks were pushed up from the seabed into a wedge during the Caledonian orogeny, our mountain building area I talked about 400 million years ago. Just have a think about that. The whole southern uplands are effectively the stuff that got pushed to the side as the main mountain ranges were being formed. This slide shows one of the many Scottish waterfalls called the Grey Mare's Tail. You can see the rather nice path going up the side here. I climbed up and you can get to the loch at the end. Not too hard a walk. Well, that was quite hard. Once you get up there, it's really nice and quiet and peaceful. Recommended for a nice day. As we've seen on the plate tectonic slide, the Earth's surface moves around slowly but constantly. Glasgow was on the equator about 300 million years ago and was a tropical swamp. We know this is true because the type of tree found in fossil grove that I showed you earlier could only grow in swamps. These swamps must have been huge and lasted for millions of years, since the Scottish lowlands have been a major source of coal, which, as we know, is just the fossilized remains of plants. I was touring up north looking for interesting things to see and dropped in on the Lochinver Geopark Visitor Centre to see if they could help me. I knew there was an interesting feature known as the parallel roads up north somewhere, but didn't have any geology books with me, and I didn't really have a good internet connection at that time. I asked if they knew where they were so I could go and visit them. Sadly, they were unable to help me, so I had to give them a miss. Once I got home, I found out they were in Glenroy. Rather embarrassing, they're in the glen that shares my name. Glenroy means the Red Glen, and it's actually further south of Loch Inver, down near Fort William. The following year I did go there, using the road from Roybridge. The parallel roads of Glenroy are these long terraces that formed along the shorelines of an ancient ice-dammed loch. The loch existed during a brief period, some 900 to 1100 years in duration, of climatic deterioration, during a much longer period of deglaciation, subsequent to the last main ice age. From a distance, they resemble man-made roads running along the side of the glen, hence the name. Charles Darwin visited the glen in June 1838 and concluded that the shorelines were raised beaches of marine origin. This was contrasted with Louis Agassiz's glacial theory, which stated that the Glenroy shorelines had been cut by freeze-draw processes of loch ice during the maximum extent of glacial ice in the climatic reversal known as the Loch Lomond Advance. Darwin defended his paper over many years. However, after reading another paper by Charles Lyle in 1862, Darwin finally relented and said, "My paper is one long, gigantic blunder." Here's another interesting point about Glenroy. Ice is heavy, very heavy. During the final stages of the last ice age, ground that had been ice-free in the north of the UK was again covered by major ice sheets. The weight of the ice made Britain into a seesaw, with the north being pushed down and the south lifting up. Obviously, this was a very bouncy seesaw, so the UK is still subject to an isostatic rebound in the north, with sinking in the south. Not good for the Thames Barrier. Just joking a bit there. Thames Barrier will have crumbled to dust long before the uplift makes any difference to it. However, as I said, Glenroy helps understand this phenomenon, since there is a slight angle of difference between the levels of each road due to the increasing pressure of nearby ice as they were formed. Most of what we looked up till now has had a very direct Scottish interest, but I'm now going to spend a short time talking about some huge geological events which were more global in extent. So this isn't too big a shock, we'll ease our way into it by looking at a rock found in Islay. This rock is called a Tillie. The way Tillite is formed was first described by geologists working around Islay. It formed between 800 and 600 million years ago in shallow water when glaciers melted and dumped all the grit and rocks they picked up. This rock's almost a kilometre thick on Islay, so there must have been a huge number of glaciers forming then melting, all at the same margin over millions of years. It was later confirmed that you'll find Tillite of the same age at places all around the world. So how could that be? Geology quite often has contending theories to explain events, and here's a good example of one. So according to the slide, it says there was an extended cold spell and the ocean started freezing. Lowered reflectivity causes further cooling, ending a snowball Earth. Well, I think that's a mistake. I think they meant heightened reflectivity, and more of the sun's rays were reflected back into space, which caused further cooling. The carbon dioxide cycle in the ocean stops. Carbon dioxide outgassed by volcanoes started to build up. Strong greenhouse effect melts the snowball Earth, resulting in hothouse Earth. CO2 cycle restarts, pulling carbon dioxide back into the oceans, reducing the greenhouse effect back to normal. So that's one way of looking at it. So this slide shows the continents separately. Some people think the snowball Earth happened at the time of the single supercontinent Rodinia. Today, the Gulf Stream carries warm water from the equatorial region and transports it to the North and South polar regions. We call this the North and South Atlantic Conveyor. And it's incredibly important since the current distributes nutrients throughout the oceans, as well as distributing heat. This keeps them warmer than direct heating from the sun would, and averages out global temperatures. Because the supercontinent of Rodinia was all equatorial level, this meant there was no gap between the Americas and Europe to force circulation currents to exist. So no warm water was forced to the polar regions, and that allowed the ice caps to slowly migrate northward and southward to the equator. This version of events suggests that once the supercontinent started to break up, volcanoes formed in the rift valleys. The dark-coloured magma and dust from volcanoes covered the ice, which warmed and melted. This wouldn't have been one continuous event because the melting water would obviously wash the dust back off again, and the number of volcanoes erupting would stop and start, stop and start. So this means there'd be many warmings and coolings over hundreds of thousands of years. And that would explain why the Tillites and Isla and everywhere else are all the same and formed at the same time, and are so thick. There's several other theories describing Snowball Earth. You just have to choose the one you like best. This is a 2.1 billion year old piece of banded ironstone, which I think looks stunning. But why is it banded? About 4 billion years ago, the first single-celled organisms came into being. Oxygen is a reducing agent and would have immediately destroyed any of these organisms. However, about 3.5 billion years ago, some maritime organisms started to develop the ability to photosynthesize their energy requirements, giving off oxygen into the atmosphere in the process. The sea at this time contained vast quantities of dissolved iron, some of which would be deposited on the sea floor. Over time, as the amount of oxygen in the atmosphere increased, it began to be absorbed back into the ocean. And when it came into contact with ferrous iron, the iron rusted and then fell to the sea floor, building up a layer of red-coloured rock. However, once the oxygen levels became too high, it killed most of the organisms in the ocean that produced it. And we had another period where no rusting took place in the deposits that fell to the sea floor. This repeated time and time again for hundreds of millions of years. And one of the ways we know it happened is by examining rocks like these. Banded iron formations like this account for more than 60% of global iron reserves and can be found all over the world, notably in Australia, Brazil, Canada, India, Russia, South Africa, Ukraine, and the United States. This is the realmenti salt mine in Sicily. This mine alone can produce 500,000 tonnes of salt per annum, and it's only one of hundreds of salt mines in the Mediterranean Sea area. The salt layer is 40 metres thick and extends for miles. The question is, where did all this salt come from? The mine is located on Sicily, which is in the middle of the Mediterranean. The geology of the Med is highly complex, and I spent an enjoyable 60 hours at lectures exploring some of this complexity. But like most things geological, it's the way the area used to be rather than how it looks today, which tells the story. One favourite fact is that large parts of Italy, including the whole of Sicily, are actually part of the African plate, not the European plate, as the politicians would have you believe. Another interesting fact is that the amount of fresh water that runs into the Med from rivers and direct rainfall is less than the amount of water that evaporates from it. The only thing that stops it disappearing is water from the Atlantic pouring in through the Straits of Gibraltar. And that's the clue to where all the salt came from. We have good reason to believe that on several occasions, the Straits of Gibraltar were uplifted by the pressure of the African plate, colliding with the European plate, causing a dam which stopped the Atlantic topping up the water level. Over a few 100,000 years, around 5 million years ago, the sea dried up completely, and the huge amounts of salt it held created the massive deposit we can see today. It then flooded again, got dammed again, and then flooded again, several times, each time building up the depth of rock salt. And just to swing it back to Scotland to finish things off, the only meteorite impact crater to be discovered anywhere in Britain or Ireland lies beneath a large area of Scotland, centred on Lairg in Sutton. Clues to an ancient meteor impact have been found in the past, in terms of rock fragments altered by the tremendous heat and pressure generated by an impact event. However, a recent analysis has shown the magnitude of the event and the probable impact area. Evidence of the giant ancient meteorite impact was identified near Aleppo in West Ross in 2008 by geologists from the Universities of Oxford and Aberdeen. These deposits of green molten rock fragments mixed in with red sandstone are almost 1.2 billion years old. The crater is at least 24 miles in diameter, and it's calculated that the impact released energy equivalent to 1,500 billion tonnes of TNT. So Scotland had its own Big Bang. I hope I've been able to show you some interesting places to go and visit once we can move about more freely, or at least when you're out and about to look at the Scottish landscape with a slightly different viewpoint. If anyone would like to ask me anything else about this presentation, I'll do my best to try and answer.